right, thank you very much for a nice introduction. First, I'd like to thank the organizers for putting on a great conference. We've had a bunch of great talks, and it looks like there's many more to come. So I'm very happy to be here this morning. I'm going to be talking about semi-definite programming and quantum cryptography. Okay, so I'm going to start. Some of you may have seen semi-definite programming before. It seems every day when you wake up, check the archive, there's always papers using semi-definite programming one way or another. Okay. So, you know, if you haven't seen it before, maybe you're reading a paper, you get to the SDP part. So I'll say SDP for semi-definite programming. Maybe you're reading a paper, you get to the SDP part, and you just kind of skip it, take it for granted, and keep going. Okay? Or maybe some of you have co-authored a paper with SDPs in it and did the exact same thing. Okay? So I'm going to explain SDPs right from the beginning, okay? And all the applications are going to be in quantum cryptography, okay? Or related in one way or another. Okay. I'm also happy to give this talk because there's not a lot of great references out there for SDPs. Okay. So semi-definite programming, which I'll get into, it's a very mathematical concept. Okay. It's a tool in mathematics. It's not inherently quantum in any way. Okay. So a lot of the textbooks or references are very mathy. Okay. And I'll give a list of references at the end, which are geared more towards quantum. But now I'm very happy to talk to a quantum audience, okay, about this stuff. And right now I'm at the Perimeter Institute. I just got there, but I'm not much of a physicist. So if there's any physicists in the audience who see any applications of semi-definite programming, I know a handful, but if you know any, please come talk to me after. I'd love to hear about them, okay? Or in general, come talk to me after. I'd love to talk about these things, okay? Okay, here's the burning question. Should I pay attention, okay? So let me just get right to it. I'm going to give a very quick overview of what I'm going to be talking about, and then you can decide whether you want to continue listening or not. Okay, it's very early in the morning. So here's an abstract that's not going to get you too far, but quantum mechanics is a bunch of positive semi-definite things interacting with other positive semi-definite things, and they interact in some kind of linear way. Okay, so that's not a theorem by any means, but it'll get you by for a few minutes. Okay. Here's semi-definite programming. Okay, so this is quickly what it is. It's an optimization class. Okay, I hate how they call it programming because I hate programming, but I like optimization. Okay, nonetheless, everyone else calls it that, so I'm going to stick with programming. And this is a class of optimization problems that optimize linear functions over positive semi-definite things. Okay, and they can satisfy some linear conditions. Okay, so if I flip back and forth between the two slides quickly enough, you'll see the two definitions really go hand in hand. Okay? Semi-definite programming is a class of optimization problems that seems to be built just for quantum mechanics. Okay? But it's been studied for a very long time. Okay? And this is a Higgs boson or something from Monday's talk. He stole my picture. So some physics in my talk already. So if you put the two together, we're going to be optimizing quantum stuff. Okay? This is kind of like the one slide overview of what I'm going to be talking about. Okay? And sometimes that stuff is crypto-related. Okay? So where do semi-definite programs appear? Well, they appear all over the place. It's not just for quantum cryptography, although it's very useful in quantum cryptography. So here's just a quick overview of some computer science / math areas. Okay, so cryptography, going to be talking about that for a while. Complexity theory. So some of the most highly rated papers in complexity theory use semi-definite programs. It's the very backbone of the paper. Okay? Query complexity, you can't study query complexity without studying semi-definite programs, it seems. Okay? If you want to capture the exact query complexity of some function, you need to understand semi-definite programming. Okay? Information theory. Okay, so there's a lot swept in this category here. Communication complexity, discrepancy theory, all these things, you need, SDPs is very helpful to know. Okay? Entanglement theory, if you're given a quantum state or some kind of channel, you want to know whether it's separable or not, or entangled. It really helps to know semi-definite programming, because there's some very nice relaxations that often do the trick. Okay? And graph theory, this is a new thing that's been just popping up in the last few years. Okay, so this is a mathematical area, just graph theory, and then now people have been looking at quantum graph theory. Okay? And a couple physicsy ones. I know this is a mixed audience. I know there's lots of physicists, experimentalists, mathematicians, and industry, government, whatever. But here's a few physics ones. Linear optics. So there's a nice PRL paper that looks at optimizing implementations of optical gates. Okay? And this is PRL, so it's only 4 pages. 2 pages setting it up, 2 pages of STP. It's fantastic. Okay? Bell non-locality. I'm seeing STPs everywhere here. Tons of stuff. Something new, causal structures, and there's many more. Okay? So if you happen to know any more applications, especially physics, please come talk to me. I'd love to expand this list. I'm looking to do that. And even though not all of these are quantum cryptography, when you're reading papers, a lot of cryptography papers use bits and pieces from these different areas. Okay? Especially in device-independent cryptography, you see a lot of Bell non-locality happening. Okay? So it's kind of creeping up all over the place, indirectly, one way or another. Yep. So this is the way I like to look at semidefinite programming. It's really a tool. Okay? It's, like I said, it's not inherently quantum itself, but it's a nice tool that you can use to tackle your quantum problem or other problems. Okay? So during this talk, I'm going to try to answer these particular questions about semidefinite programming. So first, I'm going to actually define it. I've been talking about it for a while now, but what actually it looks like. What should I do if I have an SDP? Okay. Once I have it, what do I do? And how do I solve it? Okay. So this could be one thing you do once you have it. More importantly, what can I solve with SDPs? You might have a problem already lined up that you're studying, and then you find out, hey, look, an SDP can solve this, and then you're good. And how can I prove things using SDPs? So it's a little bit different, how to prove something and how to solve something. Okay? And those will be the 2 parts of my talk. Okay? A little more practical. If I have an SDP in my paper, what will a picky referee make me check? Okay? So I'm going to kind of point out some common mistakes and some little subtle issues that I often pick out whenever I'm looking at a paper. Okay? So that I can make him or her happy and leave me alone to avoid multiple rounds of review so I can get my paper published. Okay? So this is hopefully 1 round and you'll be done. Okay? Okay, so part 1. I'm going to introduce semidefinite programming. I'm going to show you some hopefully interesting semidefinite programs, some that may interest you. Okay? And I'm going to be talking how to solve them. Okay? So it's going to be split into 2 parts. Most people, when they have an SDP in their paper, all they want to do is find the solution. They have a particular problem. They cast it as an SDP. They solve it on a computer or by hand or whatever. They get the solution, and then they go on their way. Okay? This is how most people use it, and this is what part 1 is going to be about. Part 2 is going to be looking at, if you have an SDP, how to prove something with it. Okay? Where you don't care about solving it, you just want to prove something interesting. Yeah? So what is a semidefinite program? So a semidefinite program looks like this. So soup, so you want to maximize some linear function, C of x, okay? So let me just kind of pick apart what's going on here so everyone's on the same page with notation. So you want to maximize this inner product. This is the Hilbert-Schmidt inner product, and it's just the trace of C star x. So I'll use a star here instead of a dagger, but it will not matter because everything is going to be Hermitian anyway, so you won't see it again. But this is the definition. Okay, so it's a trace of C times x. Okay? This notation means positive semidefinite. Okay, so it has non-negative eigenvalues and it's Hermitian. C is also Hermitian, you can assume this. If it's not Hermitian, then you have problems with the inner product being complex. And optimizing a complex number is kind of funny business. Okay, so we just assume it's Hermitian, so the inner product is real. B is Hermitian as well, and A is going to preserve Hermitian matrices. So if you input a Hermitian matrix like X, you get out Hermitian matrix. And it's linear. It's very important that it's linear. Okay? Don't worry too much about the hermiticity preserving. Usually when you cast these STPs, it's usually the case anyway. Okay? Because if they're not, it's quite ugly. So X is the variable. X is the thing that you're seeking. You don't know what X is, and you want to find the best choice of X. So that's the variable. And A, B, C is the data of the SDP. Okay? So I'll begin to some examples, but basically, if you give me A, B, and C, I would stick it into this semi-definite program, I would solve it, and give you back the best X. Okay. And this guy up here is the objective function. This is the function that you actually care about. Okay, this is what you're trying to optimize, and these are your constraints. Okay, you want to optimize over X, but you only care about certain choices of X. Okay, and the certain choices of X have to be captured by these conditions here. Okay. So here's a quick geometrical picture. Some people much rather look at this than the algebra. So right here you have some kind of nice set of matrices. Okay, in this picture, think of them as the set of positive semi-definite matrices. Okay, and this is kind of a cone, but it goes up forever because you can scale these things, and it's all filled in. Okay, so it's a nice convex set. So that's the set of PSD matrices. This right here is an affine slice. Okay, so it doesn't have to go through the origin, but it's basically a linear subspace that's kind of shifted over. And the intersection is exactly what we care about. Okay? So if it's in this cone and in this slice, then we say that it's feasible. Okay? And so these are the things we actually care about optimizing over. And the set of all feasible solutions is called the feasible region. Okay? It could be small, could be big, could go up forever, or whatever. Okay? Okay, so those are a bunch of definitions I just threw at you. Okay? But now let's go through some baby STPs and kind of iron out, see what they actually look like, what's happening. Okay? So here's some baby semi-definite programs just to get us going. Here's a very easy one. So soup is just a fancy word of saying maximize. Maximize the identity inner product with X. So this is just the trace of X. Okay? Subject to X equals the identity, and X is positive semi-definite. Okay, so this is totally fine. We have this nice positive semi-definite constraint here. We have X equals identity, which is a very hard constraint, but it's fine. It's linear. Everything is fine. Okay? Right here, this is the feasible solution is X equals identity. It's also the optimal solution right here, because there's no other choices. You cannot do any better. And the optimal value is 5, because once you stick in X equals identity up here, calculate this inner product, you get 5. Okay? So now we have an optimal value and an optimal solution. Okay? I call this the vegetarian problem, because in Canada, usually what happens, I go into a restaurant, look at the menu, and there's about one vegetarian option. Okay? So it's very easy to find the best solution. I'm not saying the optimal solution is very good, but you're finding it quickly. Okay? So that's a vegetarian problem. Okay, so right here, this is the exact same thing, except instead of a plus identity, I have a minus identity. Okay? So right here, X equals minus identity is the only thing that's going to satisfy this top constraint. But this has to be positive semi-definite. So there's no choice of X that's going to satisfy both of them. Okay, so no feasible solution exists. And the optimum value is minus infinity. Okay? So minus infinity, it's kind of a convention. If you optimize over, or I should say maximize over the empty set, the optimum value has to be minus infinity. Okay? It's a convention. If you don't like it, don't worry about it. It's going to creep up a little bit later in the computations, so I just want to throw that out there now. Okay? So that's infeasible. Okay? I just relaxed this constraint. Now I have greater or equal to identity. Okay? So what this notation means, X minus identity has to be positive semi-definite. Okay? So right here, this one has a feasible solution, X equals identity again. Identity is my favorite matrix, if you couldn't tell. But no optimal solution exists. Okay? X equals identity is feasible. X equals 2 times the identity is also feasible. Same with 3 identity, 4 identity, and so on. Okay? So you can get better and better. This objective function can increase forever, and there's no bound on it. Okay? So that optimal value is plus infinity, since we're maximizing. And we say that this is unbounded, okay? Because there's no bound. And this one is, I just changed this soup up here, or over here, I guess, to minimize. So infimum is a fancy way of saying minimize, okay? This right here, but now X is larger identity. And this also has a feasible, it's feasible because X equals identity satisfies the constraints, and it's a finite value. Okay? So even though over here we had this feasible region that was very large, there's no bound on it, there was no optimal solution, but over here there is, because you're just kind of heading in a nice direction. Okay? So you can maximize or you can minimize. It's up to you. Here's one more baby example. I kept talking about soup and max and inf and min. This is why we actually need to use these funny words over here. So here's a very nice SDP. It's very small. Okay? So you want to minimize this real value t. And you have a 2 by 2 PSD matrix, and t shows up in the top left corner. S is the other variable, and these guys are forced to be 1. If this guy's positive semi-definite, we have to have t greater or equal to 0, okay? Because the diagonal always has to be non-negative. However, t equals 0 is impossible, okay? If you stick in 0 there, there's no value of s that'll make this positive semi-definite, okay? You can check this quite easily. However, you can get t very, very, very small, okay? So for any positive value of t, right here, this guy, you can set s equals 1 over t, and you're totally fine, and you get a feasible solution. So this guy can get arbitrarily close to 0. However, you cannot get exactly 0. Okay? So that's why there's an imp here. The infimum is 0, but there is no minimum. Okay? So minimum means that you cannot do any better, but any choice of t you give me, I can always get better. Okay? And it's a very subtle thing. And I know physicists couldn't care less about getting arbitrarily close or exact. But later I'll tell you why this is very important. Okay? It's very subtle, and it's probably not going to change your life at all. But I'm going to tell you a story anyway. Okay? So those are some baby examples to sort out optimal solutions, feasible solutions. Now let's get to some quantum problems. Okay? So these are not necessarily going to be quantum cryptographic yet, but they could be used in quantum cryptography. Okay. So optimal quantum states. So there's lots of things that float around when you're studying quantum. You can have states, measurements, channels, all these kind of neat things. Let's optimize each one. First, optimal quantum states. Suppose you're given some measurement, some POVM. Okay, there's two outcomes. It's either accept or reject. Okay. The task is find the quantum state that's going to maximize the probability of acceptance. Okay? So you could think of this as being some kind of measurement at the end of some cryptographic protocol or whatever, and you want the person to accept what's happening. Okay? So this is a very easy problem, but let's cast it as an SDP. So what's the data? Well, what do I need to know before I start solving things? The data is just basically this one POVM element right here, pi accept. That's the guy we care about. Since there's only two outcomes, we know pi reject has to be the identity minus pi accept. So pi accept is basically everything we need to know. The variables are density operators, k rho. Now, if you want to formalize this in a mathematical way, we need unit trace, and rho is positive semi-definite. If we have those two conditions, they're necessary and sufficient. So this exactly captures the set of quantum states. Okay? And the objective is we want to maximize the probability of acceptance. So given any quantum state, the probability is going to be this inner product right here. So we could throw all those things in an SDP. And we're maximizing a linear function. We have this nice affine constraint, trace equals 1, and it's positive semi-definite. Okay? So this is a very easy semi-definite program. Okay? Nonetheless, we're optimizing quantum states already. Okay? And the optimal value is the largest eigenvalue of pi accept. Okay? So could be a projection, in which case it's just 1, but it doesn't have to be a projection. You can do this for any POVM. And now you get the largest eigenvalue. Okay? So this is an SDP that you can solve very easily. Okay? In fact, if I asked you this question before, you could probably solve it without SDPs. Okay? It's very easy. Later, I'll show you how to actually rigorously prove that this is the case using SDPs, but that'll come in the second half of the talk. Okay? So we've optimized over quantum states. Yes, quick detour. So there's different kinds of quantum people. There's mathematicians, computer scientists, experimentalists, whatever. But I find there's always one thing they have in common. Maybe some of you will disagree with this, but the fidelity function. Everyone loves fidelity. Experimentalists can't get enough of fidelity. High fidelity gates, high fidelity this, high fidelity that. Everyone loves fidelity, okay? So here I'm going to calculate the fidelity function between two quantum states. So we have rho, we have sigma, and this is the fidelity. This is the definition I'll use. Okay, some people put a square there, but it doesn't matter. This can still be cast as an SDP. And you can look at it like this. Okay, I won't go into the derivation. Basically, you have this big block matrix here. Rho and sigma are the two states you want, so you just kind of throw them in the top left corner and the bottom right corner. And x is now basically your variable. So you have x up here. Downstairs here, you have x star. X is not Hermitian anymore because it's in the funny part of a Hermitian matrix. Okay? So this guy is PSD. And this, depending on what x and x star are, you take the trace to get the fidelity. Okay? So this was proven about 5 years ago. And the neat thing, I found two references for this. One was by a PhD student in physics. Okay, talking about, so you can find it in this thesis right here about benchmarking optical circuits. Okay, very physicsy. It's also in a paper of John Watrous. And the title of this paper is Mathy, Math, Math, Math. Okay, very different worlds, very physicsy and very mathy. Okay, so I think it's very handy to have this SDP independent of what you're studying. Okay, because fidelity is very important. Now, you may be thinking, why do I need this SDP to solve fidelity? Okay? If I have some small quantum states, I could just calculate by hand. Or if they're large, I'll just get Matlab to do it for me. Why go to all this bother? Okay? Well, the thing is, sometimes, right here, you don't know exactly what rho is. Rho could come from some kind of set. Sigma could come from some kind of set. Okay? And sometimes you want to search both of these sets to find the maximum overlap. Okay? You want to choose the best rho and the best sigma such that they give you the best fidelity. And now if you don't know what the best rho and what the best sigma are, you can't just solve it on Matlab. Well, you can if you use SDPs. Okay? And this is exactly what was done in this paper by John Watrous. Okay? So if you range over the particular choices of rho and sigma here, then you can start calculating other neat functions, like the diamond norm, or completely bounded norm, as he calls it. Okay? So I think this is an SDP that's very handy to have. And there's other SDPs actually for the fidelity function as well, based on Ullmann's theorem or whatever, but this is a very nice one. Okay. Optimal measurements. So I talked about optimizing over states. Now let's go to measurements. Here's a very nice problem that I find very clean. It's this quantum state discrimination problem. In this, you're given there's a handful of states, and you know what these states are. And someone is going to pick one out of the box and give it to you. Okay? They might give you rho 1, they might give you rho n, whatever. They do this with some kind of a priori probability. So you know the probability of each one being chosen. And the problem is, once you're given this state, determine what state you are given. Okay? The data to solve this problem is just the states and the probabilities associated with each state. Okay? The variables are the POVMs. So let me tell you how I'm going to set up solving this problem. If you're given a state, what you can do is set up a measurement, and you apply the measurement. The outcome of the measurement is going to correspond to your guess of what the state is. Okay? So if you measure, you get, say, M2, then you're going to say, hey, you give me rho 2. Okay? So POVMs are the variables here. Okay? POVMs are very nice because they add to the identity, and each one is positive semi-definite. Okay? So everything is kind of OK as far as STPs are going. And then maximize this linear function. Okay? So this is going to be the minimum error measurement. There's lots of different kinds of measurements you may want to perform. But this is one. So with probability pi here, you're going to be given rho I. Okay? And with this probability is the probability that you actually output the correct thing, given rho I. Okay? So you average over all the choices, and right here, this is going to be the overall probability that you're correct. Okay? So we could just throw this into an SDP, and we're done. Maximize this linear function of these m's. They add to identity, and they're positive semi-definite. Okay? Now, there's many variables in this STP. In the STP I showed you at the very beginning, there's only one constraint and one variable. That's totally fine. You can, if you want, you can shove this into that form, or you can just leave it the way it is, and that's totally fine. You can have many variables and many constraints, and everything is cool, okay? As long as it's finitely many. We don't know the optimal value of this problem, okay? And this is kind of annoying. It's such a very nice STP, okay? And it looks like it's very easy to solve. And in fact, we're going to look at different incarnations of this STP later in the talk. It looks like it's so easy to solve, but this is an incredibly hard problem, okay? If you're given 2 states, it's easy, and 3 or more seems to be incredibly tricky, okay? So there's no closed form solution. If you give me the states, I can solve this on a computer and tell you the best measurement. That's okay. It's just if you give me arbitrary states, general states with no structure, then I can't just spit out the optimal measurement, okay? So this is a case where it's nice to have an STP, okay? And optimal measurements, you can guess, are quite handy in cryptography. Okay, imagine you're eavesdropping on a channel, okay? Suppose you're in the middle of BB84, and you're getting sent one of these 4 states or whatever. If you're able to measure and learn what the states are with high probability, then you could get all the information, just reproduce the state and send it along its way, okay? So discrimination shows up a lot in cryptography, and we're going to see it again in a later application. Oh, and the cool thing about this was proven a long time ago, okay? Way back in the 70s, okay? Done by Halevo, okay? So he looked at the structure of all these optimal measurements, but he wasn't using semidefinite programming, okay? He was just using convex programming, which was kind of the thing to do back then, okay? So it's a more general class than semidefinite programming. Okay? Semidefinite programming didn't get popular until about the 1990s. Okay? So someone came along, or Gomans and Williamson came along. They had an NP-hard problem, and they were able to approximate with STPs, and the computer science community just blew up. They're like, oh my God, now we can efficiently solve these really hard problems. Okay? And then ever since then, people started really caring about STPs. Okay? So this guy's pretty cool. He was doing it way before HTTPs were popular. And these are some early references for the first time STPs explicitly were used in this problem. Okay. So I can't talk at QCrypt without talking about cloning. Okay? So we have all these sheep. It's kind of the official mascot. And now we want to talk about cloning. And in fact, yeah, so there's already 2 cloned sheep behind me here. They couldn't help themselves. I'm going to talk about cloning quantum states. Okay. So this is very similar to the quantum state discrimination problem, except it's a little bit softer. Okay. So suppose you're given 1 of n pure states now. I'm just going to make them pure just because it makes it a little cleaner, with probability pi. Okay, so same setup as before, but instead of learning what state you're given, you just want to clone it. It's a little bit softer. Yeah. And why do I say it's a little bit softer? Well, if you're able to perform a measurement and correctly learn what state you're given, then you could just make as many copies as you want, and you're done. Okay? So here you don't need to extract any information, you just need to clone it. So it's going to be very similar. We're going to have the data is, again, the states and the associated probabilities. Okay, same setup. But now we're going to optimize over quantum channels. Okay? So imagine you have this magical box. You put in a state on X right here, and you want to output 2 copies of that state. So right here, Y is really just 2 copies of X. Okay? I just kept it as Y to keep things clean, but that's all it is. This magical box can be characterized by a quantum channel. So right here, we're just going to optimize over the set of quantum channels. Now, quantum channels have funny beasts. I want to optimize over matrices, not channels. Okay? And there's lots of ways to characterize the set of channels, but I'm going to use this one, which maps it to matrices. It's very nice, the Toyama-Minkowski representation. Basically, if you give a channel, you map it to a matrix in some kind of bijective way. So if I give you the matrix, you can also tell me what the channel does as well. So it goes back and forth. The constraints are if the channel is the channel is completely trace preserving, no, completely positive. Completely positive, then the matrix has to be positive semidefinite. Okay, that's if and only if. And if this is a trace preserving channel, then you have this linear condition on the representation, J. Okay, so this is the partial trace, and it has to be the identity. So this matrix acts on X tensor Y. It's going to be a very large matrix. Okay. So as long as you have a matrix that satisfies these two conditions, this is necessary and sufficient for a quantum channel. Okay. Now the objective, you could think of many different kinds of objectives that you may want, ways to measure the success of cloning, but this is one I'm going to use. It's quite clean. So you're given with probability pi, you're going to be given this state psi I. Okay? And you want to input it into the channel right here and expect 2 copies of the same state coming out. Okay? And the way to measure this, you could use the fidelity or the inner product or whatever, and you're just going to compare it with 2 copies of the same state. Okay? So it's kind of like I'm playing a game. I'm going to prepare a state for you. I'm expecting 2 states back. Okay? And I'm just going to perform some kind of measurement to check. Okay? Now, I can't write the STP just yet. Now, why is that? Well, these are the constraints I want. I wanted matrices. And I did a bit of work to make this happen. Right here, I just have channels. Okay? So they live in different lands. So what we're going to do, so we're going to take this and clean it up. Okay? So I just rewrote it up there. We can use this property right here. So if you want to input a pure state and compare it to a pure state, this works for any states, then you can just write it as this larger inner product in terms of its representation now, J. So now we've taken this channel, and now we have the matrix, and we're just about done. You just kind of clean this up. So clean, 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 clean. And this is the inner product between the C matrix, which I'll get to, and J, which is the matrix variable we wanted. Okay. C just ends up being this guy. Okay, so it looks a little nasty because it takes up almost a whole slide, but it's pretty clean. We just have the states and the probabilities. Okay, and this is the complex conjugate. Okay. So take this value of C. Let's go back to the previous slide, right at the bottom here. And now we have a very nice STP. Okay, so start off a little nasty, but we cleaned it up. And then we have this, and this is a very simple STP. It's very nice. Okay, so J is the variable here. It's a funny choice of a variable, but it's the variable. So PSD, some kind of linear condition here, and maximize CJ. Okay, so it's very clean. Okay, and this particular STP representation is in this paper down here. And if you want other kind of merits of cloning, you can look at the references in this paper. They have a nice discussion. Okay, and there's many more. Okay, but I like these particular examples because you can optimize over quantum states, quantum measurements, and quantum channels, okay, which are kind of like the 3 things that form quantum mechanics. Okay. Okay, so I'm going to be talking about 10 minutes or so on how to solve these things. Okay, so if you're working along and you actually say, hey, look, I have a particular state, a set of states that I want to discriminate, okay, or I want to actually clone a particular choice, how do I get the optimal solution? How do I learn what the optimal cloning machine is? Okay? So, STP solvers. Step 1, get Matlab. Okay? So you can go to this website and pay thousands of dollars, or just email your IT guy and he'll just hook you up. All right? Go to this website. So this is the STP solver I recommend everyone to use. So it's called CVX. Okay? So CVX, if you want, you can write that down and give it to your grad students. It's what I recommend. It's very good. And thanks to Grant and Boyd, they're the ones who take care of this. During my PhD, I was using STP solvers that were just really, really nasty. You basically had to take a course in optimization just to understand how to fit like the data into the computer to ask it to solve. Like they were really nasty. CVX, what it does is takes all these nasty programs. I shouldn't say they're nasty, they're very elegant. But I don't want to be mean or anything. They're very nice, but it's kind of hard to ask the computer to solve them. Okay, so CBX is a front end to these things. Okay, and I'll show you some programs in a second, and how clean they are. And it basically asks these nice algorithms to solve it for you. Okay. And I should just mention at the bottom here, there's going to be more implementations coming soon, I hope. And these have been in the works for some time now, so don't hold your breath. But eventually they'll come out on R, whatever that is, Python, and C++. Okay? But right now, as far as I know, it's only on Matlab. Okay? So sorry, mathematical people out there. So I'm going to go through some baby examples just to set it up. And then I'm going to solve some interesting quantum examples. Okay? So let's take this, the first of the baby STPs. It's feasible. It has a very easy solution. Okay? And let's look at how easy it is to solve. So this is the C matrix here. So I'm just going to set C equal the identity. Okay? So I is the cute way Matlab likes to do identity. And then you're just going to tell the Matlab program, hey, start solving STP. Okay? Because CBX can solve many different kind of nicely structured convex optimization problems. But you're going to say, hey, look, STP. Okay? You initiate the variable. So you have a 5 by 5 Hermitian matrix. So this can handle complex values. That's totally fine. Maximize the trace of x times c, which is exactly this. X equals the identity, x does posit semi-definite, and then you're done specifying the STP. Okay, so it's very clean. This is basically how you'd write an STP if you're just emailing someone. Okay? And then I have it spitting out the optimal solution, optimal value. Okay, so it's a very short piece of code, and you can use it, and it spits out all this stuff. So it solves it. Okay, so that's good. If we couldn't solve this problem, it'd be something to worry about. So right here, the status is solved, okay? And it gives you the optimal value of +5. And I have it spitting out the optimal solution and the optimal value just for my own sanity, okay? So you should always check the output, okay? Don't just trust any algorithm to give you something and you just kind of run away with it. Always check it, okay? So, you know, I have it spitting out the optimal solution, and then you can check it equals the identity, and it's posit semi-definite, so everything's fine. Okay? If you care to read all this stuff, I don't think anyone does, but this says how good the algorithm performs. Okay? I'm not going to talk about what all these things mean. I'm going to kind of get to it later in the talk, what these mean. But basically, if they're close to 0, you have a good solution. Okay? If they're far away from 0, then it struggles a little bit trying to solve it. Okay? I should say these solvers are not commercial. They're not at the level of being commercially available. They're really just you download them in Matlab and play around. Okay? So close to 0 is good. I'll talk about what those mean a little bit later. Here's another one that's infeasible. Okay? So basically, I just put a minus sign on the identity here, ask it to solve again. And this is what it shows. So it's infeasible. Okay? It's infeasible, and here's the minus infinity thing showing up again. Okay? That's why I mentioned it before, because the output is going to tell you minus infinity. Okay? The optimal solution, optimal value, is NaN, which means not a number. Okay? So that's basically MATLAB's way of saying, yeah, I don't like it. Okay? There's nothing there. Okay? So we did a good job on this. Let's look at an unbounded example. Okay, so right here, x is larger than the identity. So up here, I just put this larger or equal to right here, ask it to solve. Oh, I left a minus sign there. It doesn't matter. Same thing anyway. Now the status says unbounded, and this optimal value is plus infinity, okay, which makes sense. But here's one thing that I caution some people. If you don't see this and you just have it outputting the optimal solution, it's going to give you something. Okay? It's a computer. It doesn't really know what you want. So it gives you some feasible solution, and it's saying the optimal value is 1. Okay? Because at some point, the algorithm just terminated. It knew it was infeasible, but there was still some value at that point. So the optimal value is not 1. It's plus infinity. Okay? So if you don't look at all that stuff that's happening above, you may be tempted just to take this and keep going on with your day. Okay? So it's really good to have at least a quick look at what your STP solver is doing. Okay? And here's another baby example. X is larger than identity, but now I have an infimum here. So you can just write the word minimize. You don't have to do any weird messing around with the optimization problem. Just write minimize, and it solves it. And you get +5, and everything is totally fine again. Okay, so this is very similar to the first thing you solved. Okay? And those things are close to 0, so everything's fine. Okay, okay, so now I want to, those are the baby examples. Okay, now I want to talk about some interesting quantum examples. Okay, so these are some things you may actually need to solve on your computer if you're doing quantum research. Okay, and these Matlab programs are available on my website, so if you want to go on and play around, feel free. Let's look for the optimal acceptance probability. Okay, right here I just have this very nice example. This is the 0-0 projection. Okay, if it's in the 0 state, it's going to accept. If it's in the 1 state, it rejects. So I have a 2x2 Hermitian matrix. I want to maximize the inner product, trace equals to 1, blah, blah, blah. Nice STP, you solve it, +1. Okay? So for those who didn't know, the largest eigenvalue of the 0-0 projection is +1. Okay? So we're off to a good start. Here's the fidelity function. So let's see how easy this is. What I'm going to do is set this thing to be one big block matrix Y. Okay? And so Y is going to be my variable here. The top left block, I just set equal rho. And the bottom right block, I just set equal to sigma. Okay? This C matrix basically just picks out this linear function of Y, and you ask it to solve. Okay? Of course, you can't just solve you can't get a closed form solution, so I just put in some states, so the 0 state and the plus state up here. And we calculate, and we get the fidelity of the plus state and the 0 state. Okay? Very easy, but we have 1 over root 2, so everything is nice. Okay? If you wanted this row here, if you wanted, you could just keep adding some constraints here. Okay? You could say the partial trace equals this, or maybe some inner product with some other POM element has some particular value. You can just, as long as it's linear, you just keep throwing them in, and then you can optimize. Okay? So we can calculate the fidelity, optimal states. Now let's look at optimal measurements. Okay? So let's pretend we're an aggressive Eve in a BB84 protocol, and we want to measure the BB84 states as they go from Alice to Bob. Okay? We want to learn exactly what it is, because we're greedy Eve. So here's the 4 BB84 states. Here is the variables, the measurements. So we have 4 states, so we need 4 measurement outcomes. So that's M1, M2, M3, M4. And we just maximize this. This is the probability of correctly guessing which BB84 state you're given. Okay? Each one given with uniform probability. They have to sum to the identity, so you just write it as you would in email. And each one is positive semidefinite. Okay? And if you solve this, you get 1/2. So there's a 1/2 probability that Eve is going to correctly guess what state you're given. Okay? And this is just sending 1 of 4. Okay? This is not sending many, just 1 state. Okay? So not very high probability. Optimal cloners. What we're going to do is take the set of states we had before, but instead of trying to learn what state you're given exactly, we just want to clone it. Okay? Suppose Eve just wants to make a copy for herself and then send the state along to Bob. Okay? So again, we have the BB84 states up here. Just write down the C matrix as I showed you earlier. Okay? And basically right here, this captures the partial trace. Okay? So depending on what system you're tracing out, it's just a linear function. But in this case, it's very nice you're just adding up some diagonal blocks. Okay? So you can do that on Matlab, no problem. And this is basically the very first application of quantum cryptography. Okay? So Wiesner's paper back in the 70s, one of the first papers on quantum cryptography, or the first paper, had two applications. One was quantum money, and one was multiplexing. Okay? So this is a very old cryptographic example. Basically, what you're going to do is put some qubits on a banknote or a coin or whatever, and you do not want anyone to be able to forge it. Okay? Create multiple copies. So what I just presented is you put one of 4 BB84 states here. Let's just say a single qubit at this point. Okay? And you want to make a copy of it so that you have more money. Okay? Very easy. So let's see how successful this is. Okay? So this is the SDP. Here's your money. Suppose you try to clone it. Doesn't quite work. You don't get 40 pounds at the end of the day. But you could do this with probability 3/4. Okay? So with 3/4 probability, you can now clone. So it's okay probability, I guess, depending on how much money you have on stake. But remember, I said this was a softer condition than discriminating. So if we wanted to perfectly learn what state we're given, it was probability 1/2. But now we just want to clone, so now we have 3/4. Okay, so it's a higher probability, as you may imagine. So 3/4 is not very secure. I don't think banks will go for this. Let's look for parallel repetitions. Okay, suppose we have, instead of putting 1 qubit on your quantum money, let's say we have 2. Okay, and then we'll worry about more later. So here's the bigger example. First, let's think of some strategies that we could employ. If you have, these are going to be independent. So with one uniform probability, you put a BB84 state here, and over here, independently, you put another BB84 state. Okay? One thing you can do is just optimally clone one, using the optimal cloner we just solved for, and then you can optimally clone the other one. And that'll give you probability 3/4 squared. But perhaps we want to do something more clever. Suppose we want to just take in both the states, perform some big cloning machine, and then spit out 2 copies. Okay? And there's nothing ruling this out. Okay? This is valid. This is a quantum mechanical strategy. Everything's fine. So let's solve this. Let's solve for this bigger instance. So now we have a big C matrix. But basically, it's the exact same thing. It's just a little bit more stuff to put into your SDP. We have this larger partial trace here, equals identity on 4 now. And we solve this. It's solved, and we get exactly 9/16. Okay? So what this is saying is even if you perform this larger cloning device, the best it can do is just clone on one and then clone on the other. Okay? There's no advantage to having this larger device. Okay? And then the success of cloning the n-fold repetition is exactly 3/4 to the n. Okay? And this was proven in the same paper that I mentioned earlier. Okay? If there's enough time at the end of my talk, I'll talk about the proof of this. It's called the product theorem, and it's very nice, and STPs are very useful. Okay? So the quantum money is safe, okay, because now we have an exponential decay. Okay, so now we solved some interesting STPs on Matlab. Now I want to talk about, suppose you don't want to solve them on Matlab. Suppose you don't know the structure of what you're trying to clone or discriminate. You just want to look at the STP, stare at it for a long time, have some fun with it. Okay, so now we're going to look at the second part, how to prove stuff. We're not solving them anymore. Now, to prove things, basically, a powerful way of looking at STPs is duality theory. Okay? And what is duality theory? Well, you have one STP. Let's double our fun. Let's look at another STP. This is the dual. Right here, you want to minimize B in a product with Y. So this is the same B over here. So he just gets upgraded upstairs here. Y is a new variable. S is another variable. The C comes downstairs. So these guys kind of switch spots. And this is the adjoint of A. I'll get to that in a sec. So the first guy gets upgraded to primal STP. He's just not STP anymore. Okay, so now we can refer to them as the primal and the dual STP. And this is the adjoint that I was saying. So we have A, which is a linear operator. Over here, A star is the unique linear operator satisfying some condition up there. But A uniquely defines A star, and A star uniquely defines A. Okay, so basically all the information over here has been shifted over here in one way or another. So they share the same data. But this guy has two variables. Y is just Hermitian, but S has to be positive semi-definite. Okay, so it's still nice. Okay, so a lot of references that you'll read, they introduce an STP and immediately go to dual STP. Okay, and I think this is kind of like, it's very beautiful, but it's a lot to take in all at once. Okay, so I've kind of shifted all this talk about dual STPs and all this theory towards the end of my talk, because most people just want to solve them. Okay, so the first half of my talk is exactly what you need for that. So what's up with this dual? Why am I complicating things? Why this extra STP? What's it going to do? Well, it's really nice. What we can do is use it to bound things. Okay, so here's the primal STP here. Here's the dual. Suppose X is primal feasible. So now I'm going to be, before we just had feasible, now we have primal and dual feasible. Okay. So X right here satisfies these constraints, and Y and S together as a pair satisfy these two constraints. Now we have something called weak duality. This inner product minus this inner product is going to be non-negative. Okay? So what's this? The value of the dual is always going to be larger than the value of the primal. Okay? And these equalities here, which I didn't really get into, they basically just follow from these constraints. It's really just that. So there's kind of two interesting things to say here. The dual is a minimization problem. So what you want to do is make this as small as possible. The primal is a maximization. You want to make this as large as possible. So you're pushing this down, you're pushing this up. Weak duality says they'll never cross each other. Okay? In the best case, they'll meet each other. This is good. Sometimes there'll be a bit of a gap, but they'll never cross. Okay? So you can use them to bound each other. If I give you a Y and S, and I calculate this inner product is going to upper bound everything up here. Okay? And upper bounding and maximization problem is a hard thing to do. Okay? So it's very nice. And this guy right here is called the duality gap. So whenever you make this as small as possible, make this as large as possible, whatever's left over is the gap. We want a zero gap. Okay? So they bound each other. So let's look at our easiest quantum example. So right here, I said before, you can get a solution that gives you the largest eigenvalue of pi except. Okay? The feasible solution is just some kind of projection onto an eigenspace, whatever. But let's prove that this is the best we can do using STPs. Okay? Oh yes, at this point now, it's going to be a bit of magic because I'm just going to show you what the dual looks like. Okay? Whenever you attend a talk on semidefinite programming, or attending a lecture, or whatever, this dual magically appears. Okay? What's happening is the person, whoever wants this dual, writes this down, takes 20 minutes offline to figure it out, and then they just throw it on the slide, like magic. Okay? So I usually find, at least I used to think this whenever I was attending STP talks a long, long time ago, that this was magic, and I was really dumb because I couldn't figure it out in my head, and I thought everyone else, it was so obvious. Okay? There is some work to go from here to here. Okay? But I'm not going to show you that work because I don't have enough time. If you want, you can just follow the recipe I had earlier, or come talk to me. I'm happy to, or go to STPs for you, I guess. But this is the dual. Okay? So I just threw it up there. And the optimal value is really just the largest eigenvalue. Okay, so if you set t equal to this is going to be satisfied, and now we have an upper bound on how well the solutions can be for the primal. So we said the largest eigenvalue is possible, but now I'm saying it can't go above it. So it has to be optimal. Okay, so those two things, and that's how you prove things. Now here's a question. Does the primal always equal the value of the dual? That is there zero gap? The answer is no. But sometimes it's true. And in fact, most of the time, it's true. Okay? So you can actually prove, if you look at the space of all SDPs, the set of SDPs where this fails, there's a positive gap, it's a set of measures 0. Okay? So if you're solving random SDPs for whatever reason, there's a very good chance that you're not going to have a positive duality gap. Okay? But if you're solving a particular SDP, especially ones that are related to quantum, because quantum things, weird things happen, right? You should check this, because maybe you are falling into that set of measure 0. Okay? So it's very important to check, and this is how you do it. Use strong duality. So strong duality, right here, we need something called a constraint qualification. Okay, what does that mean? Well, basically, it means that the SDP has to be modeled in a nice way. Right here, if there exists an X such that this guy right here is feasible, but X has the extra property of being positive definite, okay, so it has positive eigenvalues, not just non-negative, then you have a very nice SDP. It's strictly feasible. And if the dual is feasible, so this is feasible, this is strictly feasible, then there's zero gap. The values are exactly the same. Okay? And furthermore, this dual here will attain its optimal solution. So you can actually prove there exists a y and an s, and this is a minimum, not an infimum. Okay? Now we have the other side. You can prove the dual of the dual is the primal. So we're just going to kind of shift hands and have the exact same theorem. Okay? A constraint qualification here is whenever S is positive definite. That means you have a nice dual, and if the primal is bounded, then you have the two values are equal as well. Okay? So this is not the weakest form of these theorems. There are weaker forms, but these are the most commonly used. Okay? And if you've never seen STPs before, this is what I recommend you do. Okay? And you could just put the two together. Okay, so now we have both beefcake arms, put them together. If they're both strictly feasible, okay, this is the best of both cases, then you have them equal, and there's no supremum, there's a maximum, there's no infimum, there's a minimum. Okay? So this is the best case, but it is the hardest to satisfy because the primal and dual both have to have this property. Okay? Okay, so here's the proof of strong duality. I think I'm going to skip it. But basically, I just want to say weak duality was very easy. It's like 4 lines long. Okay? It's super easy. But strong duality takes some time to prove. Okay? If you sit down in lectures, it'll probably take an hour or so. So there's a lot going on. Okay, so let's check for strong duality in the example we just had. Okay? We already knew there's zero duality gap. We knew the existence of primal and dual optimal solutions. But let's just prove these things exist without actually solving them. Here's a strictly feasible solution for the primal. You just put in the completely mixed state. Okay? Just scale the identity until the trace equals 1. This guy's going to be positive definite, so the primal is strictly feasible. Okay? This is probably not an optimal solution, but it's a strictly feasible solution. Over here, just throw some large value of t. T equals 2 will make this positive definite. Okay? Therefore, the dual is strictly feasible. Okay? This is certainly not an optimal solution. Well, this is a POVM. So we have strong duality. We know the values have to be the same, and they both attain their optimal solution. I didn't solve anything. These were definitely not the optimal solutions. But I'm able to say something about the optimal values without solving them at all. Okay, so that's a nice thing about strong duality. Oh yeah, and like I said, these guys both attain an optimal solution. Okay? So attainment of optimal solutions, if you're just doing this numerically, then it doesn't matter so much because computers they don't do exact arithmetic anyway. But sometimes this is the difference between proving a result that's true and proving a result that's false. So in my PhD, I was working on the quantum state discrimination problem. I was having fun with STPs, all this neat stuff. And then I assumed the existence of an optimal dual solution. I knew these two values were the same, but I was assuming this was a min and non-nymph. Okay? So I did lots of nice STP work, got some kind of result, sent it to some experts, and they said, no, this is completely wrong. I'm like, okay. So I looked over all the complicated STP stuff I was doing. I'm like, where's the problem? And it ended up, I was assuming there was an optimal dual solution when there was not one. Okay? So most of the time, this does not matter, but sometimes it's the difference between having a paper and having no paper. Okay? And I was in PhD, so this really sucked. Okay. So. But most of the time, it doesn't matter. But if I see an STP in a paper, I really want people to argue. If they put a min there and they start talking about optimal solutions, they really have to argue why they exist, either with strong duality or compactness or whatever kind of argument you want. OK, so now I want to talk about a crypto application where STPs are going to be applied directly, and we're going to have some fun with them. Okay? So bit commitment. So Alice has a present for Bob. It's Bob's birthday, but the problem is that Alice is at QCrypt listening to some fantastic talks during Bob's birthday. Okay, and Bob couldn't come to QCrypt for whatever reason, so he's back at home. But Alice cannot leave the present with Bob because Alice knows that Bob will open it early. Okay? So she knows quantum bit, or whatever kind of bit commitment this is. She's going to employ it, and she's going to put it inside the box. Okay, I lost my animations, but you can just use your imagination. This is going in there. All right? This is being sent to Bob. Bob is not very strong. He cannot break the safe. Okay? So he's stuck with this big safe during QCrypt and waits till his birthday. At which point, Alice has some key, which is small, much smaller than the safe, so it sends it to Bob on his birthday. Or maybe it's a digital combination, just emails it to him, which makes more sense. Okay? Bob applies the key, opens up the safe, gets his present, and he gets his nice gift. That was too expensive to mail during QCrypt. Okay? So great success. Let's do this in an information theoretic way. This is quantum bit commitment. Okay? This is just a very simple scheme. Alice is going to have a bit. Okay? It's not a car. It's just a bit, 0, 1. She wants to send this to Bob. What she's going to do is encode it into a quantum state. So depending whether she wants to send 0 or 1, she's going to create a bipartite quantum state, one or the other, and send half the state to Bob. Okay? So Bob now has B. Okay? Think of it as being entangled. Okay? So neither Alice or Bob have complete control anymore. They only have partial information. Okay? Because they're sharing this entangled state. When Bob's birthday comes along, Alice is going to reveal what A actually was at the beginning and send the rest of the state. Okay? And this is for cheat detection because what Bob can do now, Bob knows what state he should have now because he has A and B. He has both the Hilbert spaces. He knows it should be in psi 0 if Alice revealed 0, or psi 1 if Alice revealed 1. So what he's going to do is check because he doesn't quite trust Alice. Okay? What he can do is measure the Hilbert spaces he has with this projection right here, psi A. Remember, he knows what A is now. Okay? If Alice was honest, this will pass with probability 1. And if she deviated, then there's some probability that she might have cheated. Okay? So this is some power quantum gives you by this cheat detection step. So what are the goals of bit commitment? Well, Bob should not be able to learn Alice's bit early. Okay? This is like opening up the birthday gift early. Okay? But right here, we're going to have some kind of constraint on Alice, or else it would be an easy problem. Alice should not be able to change her bit before revealing. Okay? She should not be able to send the Hilbert space B and then later be like, you know what, I didn't like A equals 0, I want A equals 1 for whatever reason. She should not be able to make this change. Okay? And these are two conflicting goals. So the question is, how much can Alice or Bob cheat? Okay? This is an example of two-party cryptography. We're not sending secret messages, or we're not copying banknotes anymore. This is two parties, Alice and Bob, and they do not trust each other. The people cheating here are either Alice or Bob. Okay? So how much can Bob cheat? Let's look at them one at a time. Okay? What does Bob want to do? He wants to learn the bit early. What he has is the Hilbert space B, and what he can do is measure B to try to distinguish between the reduced states of 0 or 1. Okay? And this is exactly the quantum state discrimination problem that I was talking about earlier. Okay? So we have an STP for that. You just look at the two reduced states up here, write down the STP, and this is exactly how much Bob can cheat. Okay? Now, it's not an approximation or anything, it's exactly how much he can cheat. Now, since we have this extra power, let's look at the dual. So I calculated the dual. Again, I waved my magic wand, okay, and I just calculated really quickly here. Now, if you stare at this dual for a while, it looks really easy to solve. Okay? X is larger than this, and X is larger than this. Why can't I find the smallest one? Okay? With real numbers, this is easy. With matrices, it's hard. Okay? It looks easy, but it's not. Okay? Strong duality holds. You can check this by finding these feasible solutions. So the values are the exact same. Okay? The values being the exact same is really neat because now this is exactly how much Bob can cheat. Okay? I didn't solve anything. I just found some strictly feasible solutions, and now I have this entirely new problem. Okay? So if someone who knows bit commitment, if I just said this is how much Bob can cheat, without going through this STP approach, you'd probably be like, what? Like, what's going on? What's this X? What's anything? Okay? And it's a good point because it's weird. This gives you a completely new perspective on the problem. Okay? So that's the nice thing about dual STPs, give you a completely new perspective. See, there's nothing quantum looking here, right? At least not that I can see. Okay, so let's just store this. So we have a dual for Bob. Let's come up with a dual for Alice. So now we have rock and roll Alice. She's going to cheat, but she's going to cheat in a way that she can decide A later. So she's not going to have some bit at the beginning, and she's not going to create the state because she's cheating. What she's going to do is send Bob some state, okay, whatever she wants. But she's going to, before she reveals it, she's going to decide at that point what she's going to reveal, either 0 or 1. Okay? So in some sense, A hasn't existed yet. And she's going to send a Hilbert space A and try to pass Bob's cheat detection. If Bob accepts the state Alice gives him, then she's succeeded. Okay? So let's say she gives some state here. She's like, I want A equals 0. So she has some kind of memory space. She applies some unitary, and then she sends the state over. If she wanted 1, maybe she applies some different unitary. Okay? So here's the variables. I think I'm going to speed up a bit. They're basically capturing the states on Bob's side. Okay? So this is the state Bob has, rho, after the first message B. The state he has after rho 0 or rho 1, depending on whatever Alice wants to reveal, has to be consistent with the state. So the partial trace of A of rho 0 has to equal rho. Okay? Alice does not have the luxury of asking for B back from Bob in order to cheat. Bob is holding on to B. She's cheating on the rest of it. She's cheating on this A component here. And then she's sending it over. Okay? So that's why there's this partial trace condition saying she cannot act on B any longer. Okay? So I'm just going quickly here. But this is the probability. So if she wants to reveal 0, then this is the probability that Bob accepts. If she wants 1, this is the probability Bob accepts. Okay? I don't want to dwell on this STP. I went a little quick there because I just want to look at its dual anyway. Okay? So STP, dual. Okay, the first one's gone. So now you want to minimize T. T is larger than this. So this is T times identity. You have Z0 and Z1 here. Okay? It's larger than these. You can check strict feasibility, so there's 0 duality gap. Okay? So this is exactly Alice's cheating probability up here. Okay? So now we have a completely different perspective on Alice cheating. So now we have a dual for Bob, a dual for Alice, and completely new perspectives. Let's see what we can do with this new perspective. Ideally, we want both these to be small. We do not want Bob or Alice to be able to cheat in big commitment. Okay? But this is impossible. Okay? It's been known for some time now. I'm going to come up with a new proof with semidefinite programming. So since strong duality holds, we know there exists an x that's optimal here. The trace of x is going to exactly capture how much Bob can cheat, and x has to satisfy these constraints. Down here, there's an optimal solution, and t is going to be exactly how much Alice can cheat. So let's take x, let's take t, and see what we can say about them. We're going to look at this product here. Let's multiply them together and see what happens. So you have this thing here. To be cute, you can write it as an inner product, like that. Okay? Just keep massaging. This inner product, t identity, is larger than z0 plus z1. So I just use that. This inequality induces this inequality. And you just keep going a few more lines, going back and forth using these conditions and these conditions, and everything just kind of disappears. You're left with 1/2. Okay? So the product on the cheating probabilities of Alice and Bob in big commitment have to be at least 1/2. Okay? Suppose you want to say, hey, look, Bob cannot cheat at all. I want a protocol where Bob cannot cheat. Okay? Well, that means he can cheat with probability 1/2, which is the same as randomly guessing. Okay? But if that's the case, then Alice can cheat perfectly with probability 1. She can perfectly decide what she wants to reveal. Okay? And so this is a new proof. It's based on Kitaev's lower bound for strong coin flipping, just a different setting. Okay? But if Bob can cheat with probability 51%, then Alice can cheat with probably at least something like 99%, something really close to 1. So you have this nice trade-off curve. Okay? And you can also generalize this to integer commitment. So you have the exact same STPs, well, almost the exact same, if Alice wants to commit to an integer instead of a bit. Okay? But instead of a bit, which is 2 outcomes, if you have an integer, you just put some integer d down here. You get the exact same bound. Okay, so no-go theorem for quantum commitment. Okay? Right here, I did not say anything about the optimal solution. I did not say, hey, this is how Alice cheats. I didn't say, hey, this is how Bob cheats. This is the measurement he uses. I didn't say anything. I just said that if Bob cannot cheat, then Alice can, just by looking at STPs and mashing the duals together. Okay, so I really didn't solve anything. So this is the difference between solving and proving. So, no-go theorem. I'm going to skip over product theorems. So this is a way of showing that optimal cloning machines, the best you can do is just optimally clone one at a time. But this holds for many, many STPs. Okay, sometimes you want to tackle multiple problems in parallel. A lot of times the best thing you can do is tackle each one individually. It's a very easy way to prove this with STPs. It works for many, many, many problems. Okay, so if you're interested in that, come talk to me during the break or whenever. I'll be around all week. But I'm going to skip over now in the interest of time. Here's a little summary. Okay, so this is what I tell people when they start working on STPs. First, find an STP. Okay, take the dual and check for strict feasibility. Okay, if you're working in quantum, this is almost always going to work. Just try the identity. The identity is a nice quantum state. It's a nice measurement. Some kind of channel I can't remember right now. But usually these things are feasible solutions. Okay? So usually you always have nice STPs. You can solve them numerically if you want. Sometimes this is all you want, which is fine. Okay? So you solve it and you're done. Sometimes you have to solve numerically to be able to find the way the problem is working. So you solve a bunch of things, you see some solutions, you stare at them for a while. Then, oh, okay, I can see this is kind of how Bob cheats in general, and this is kind of how Alice is cheating or whatever. Okay, so these kind of go back to back, hand to hand. And yeah, write a paper, make money, get a job, you know, all that good stuff. So here's some references that are nice for STPs. Okay, so you can find these slides if you want to give them to your grad student or whatever. They'll be on my website, and some Matlab programs to get started. So I taught a course on quantum and STPs, so some lecture notes. Even better, John Watrous' lecture notes. I highly recommend them over mine. So he has a couple lectures worth of STPs. Really nice, geared towards quantum, obviously. Here's some non-quantum ones that are just nice in general. So this is my PhD supervisor, well, one of them, the STP one. And he wrote this textbook. That's how I learned. It's really nice. And this one is available for free on the internet, I believe. I have a free copy. So you can find that if you just Google it. Okay? And that's it. Thank you very much.